All right, so our amplifier circuit of interest is going to be this guy. Where we're effectively going to have a single stage op amp circuit. Our input signal is going to be applied over here, and actually let me, just for the sake of argument, put in some signal resistance here. And then on the right-hand side of this circuit is where our feedback network is going to be applied. And so that's going to be a resistor R1 between our output node and the gate terminal of transistor M2. And then we're going to have another resistor here, R2, like so. So while we're at it, this is M1, this is M2, this is M3, and this guy is M4. So where is our VI signal on this circuit? So for a transistor circuit, it's always going to be either a VBE or, well, so let me rephrase that slightly. For a transistor circuit where we have voltage feedback, it's always going to be a VBE for a BJT transistor, and it's going to be a VGS for for a MOSFET transistor. This is obviously a MOSFET transistor circuit. So I'm going to say that our quantity VI is this guy right here. And then our quantity VF So I want to ask you guys what I hope to be a very simple question, but does this make sense? If we didn't have this feedback network, what would this be? I think I mentioned it.
It's I'm sorry.
There's a current mirror on top for sure. Well, what's this bit down here on the bottom? That's a differential pair.
Yeah.
Waving your hands at it doesn't particularly help. We have a differential pair loaded with a PMOS current mirror. This is literally a single stage op, right? Where we have a differential input voltage and then our output voltage taken at this point. So we're converting a differential input voltage into a single-ended output voltage. This is an op-amp. Yes, sir.
So our output voltage is divided between those two resistors and applied to the gate of M2.
Right.
Since the output voltage is diminished before it's applied, is it negative feedback?
Exactly right. That is 100% exactly what's going on. That is a perfect interpretation of exactly what's happening. Right. So we have this voltage divider network over here. On the right-hand side of our circuit, some portion of that voltage that's provided at the output gets fed back to the input port on the right-hand side of our differential pair. And that's where our feedback and input, 100% correct. Very, very good job. Okay. So since we've identified our quantity in VI, or our quantities VI and VF, and just as a heads up, I went ahead and did this for you on all of your homework problems on this kind of stuff, so you can figure out how things are connected easily. I'm deciding whether or not I'm going to do it for you on your exam as well, probably, but we'll see. So let's draw a picture of our feedback network. All right. So connecting my output, so my output side of the amplifier is always at port 2, and the input side of the amplifier is always at port 1. Between my output of the amplifier and the input of the amplifier, I see that resistor R1. And then between the input side of the amplifier and ground, I see that resistor R2. And so that is what my feedback network looks like. Anybody have any problems identifying the feedback network? It should be fairly straightforward when I take the time to tell you exactly where our signals are doing what they're doing. Okay. All right, so we need to determine our loading resistance R11 and our loading resistance R22, as well as our feedback factor. So look in your notes from Wednesday and tell me how we figure out what R11 is. Right, so we look into port 1 with port 2 short circuit for a feedback voltage amplifier. So as Gavin suggested, R11 will simply be R1 in parallel with R2. We determine R22 looking into port 2 with port 1 open circuit. So this is simply going to be R1 in series with R2. We determine our feedback factor K by applying a test source voltage across the terminals of port 2 and taking the ratio of the feedback voltage defined as the voltage drop across port 1 divided by our test voltage, which in this case is just going to look like R2 over R1 plus R2. So this should always be our first set of steps, determining what our feedback network looks like, determining our loading parameters R11, R22, and our feedback factor K. From here, we use these values to construct our open loop gain circuit, which includes these loading parameters, where R11 is going to be placed between the input port and ground, and R22 is going to be placed between the output port and ground. So for our circuit, our open loop circuit is going to look something like this. So here's V in. Here's R sig. I don't think I gave myself quite enough room, so let's make that slightly smaller. Let's see, here's our tail current source, ISS. All right, so connected to our input port, we should have resistor R11. Here is our output. We should have R22. Here is V out. And our goal here is simply to determine the ratio of V out to V in. Since this is a single stage amplifier that we've covered before, can anybody remember what this would normally look like? The voltage gain of this circuit, right? That's what we need. Our open loop voltage gain, A. So anybody remember what it's supposed to be without all this feedback crap connected? So there isn't an RD. This is an integrated circuit. So there should be some R naughts thrown in there. I heard somebody saying something. That is correct. Okay. So normally this would be GM1, and I'm going to put 1, 2 because GM1 or GM2 would work because they're identical, or at least they're supposed to be. Oh, and let me identify these. M1, M2, M3, and M4 times R02 in parallel with R04. So what effects are our loading resistors going to have on this?
Will not affect R1, so R11 has no effect.
R11 definitely not going to show up, absolutely correct.
And then R22 will be in parallel with R0.
It'll be in parallel with R04. Because R04 is connected between the drain and the source of M4. And since our source is at ground, that's the same thing here. Now, R02, the reason why this looks like R02 in parallel with R04 is effectively looking down, we see R02. Looking up, we're going to see R04 in parallel with R22. So I'm just making that distinction because mathematically it would have been the same either way, but I'm trying to make sure that you're looking at it correctly.
Right. Yeah, I was looking at the node above the current source ground.
Right.
Which I guess this isn't exactly.
So, well, that's actually not an unreasonable way to look at it as well. So that is effectively correct. When we did this analysis, we said specifically that this node wasn't ground, but it was close enough to be ground that it really wouldn't matter. So yeah, for that particular interpretation, where we're treating this node as ground because we have a pseudo-symmetrical circuit, then you could see R22 in parallel with R02 and it wouldn't particularly hurt anything. But to me personally, it's more obvious because we don't have to make that distinction if we're looking at what we see up with that PMOS transistor. But seems like it's, 6 of one, half dozen of the other, so it doesn't particularly matter. You get the same result either way. All right, so that's our open loop gain. Hopefully that was fairly straightforward. It was literally something that we had seen before. And then we had something else being added to it in parallel. Nothing wild or crazy there. What is our input resistance? So let me define these guys real quick. Here is where we're going to measure RI, because here is where we would see RIF. Here is where we're going to measure R0, because here is where we would see R naught F. So what do we see for Ri? R sig in series with infinity, which is infinity. Everything okay? Okay. Gavin, I just noticed your shirt. I like it.
It was our city series.
Infinity, which is infinity. So what do we see looking in? Well, we have this, and then we have the open circuit. That is the gate source. Looking at DC.
Do we find RI and RO after we convert the circuit?
Yes. Because we're trying to make sure that we include what effects our loading resistances or what effects the feedback network is going to have on those parameters as well. So yes. So these absolutely need to include R11 and R22. So what do we see for R not? Our output resistance of our open loop configuration here.
R naught R1 or R naught 2 parallel, R naught 4 parallel. R2.
Exactly right. Okay. So from here, we have everything we need to know to calculate, as it were, our gain with feedback, our input resistance with feedback, and our output resistance with feedback, right? Our gain with feedback, AF, will always be our open loop gain A over 1 plus KA. So for us, let's call that GM1 times R naught 2 in parallel with R naught 4 in parallel with R22 divided by 1 plus K, which we found to be R2 over R1 plus R2, R naught 2 in parallel with R naught 4 in parallel with R22. Ri, not that it's particularly going to matter. Yes. Oh, yes, thank you. I'll tuck it in here at the end. Thank you for noticing that because I straight forgot to write it down. So thank you. For RI, it's not going to particularly matter here because, or excuse me, RIF, it's not going to matter here because we found RI to be infinitely large. But we should see that the input resistance with feedback is boosted, right? So this should be always Ri times 1 plus Ka, which in our case is still just going to be infinity. And for our feedback voltage amplifier, ROF should be RO divided by 1 plus Ka. So that should be R naught 2 in parallel with R naught 4 in parallel with R22 all over 1 plus R2 R1 plus R2 times GM R naught 2 in parallel with R naught 4 in parallel with R22. On your answers for your homework, I explicitly put whatever R22 and R11 was, like whatever combinations of feedback that was, instead of leaving it as R22 and R11 and all kind of stuff. All right, so this circuit has effectively been analyzed. Anything particularly wild or crazy. All right, let's do one more. Didn't give myself quite enough room here. Let's call this RD1, this guy RD2. This guy is VSIG. I'm going to ground this guy right here. So this guy R1. This guy R2. And just to throw you guys a curveball that I want to see if you catch, I'm going to call this guy R3. This is transistor M1, M2, and M3. All right. So let's identify our input signal VI. Where's that going to be? Well, it's going to be the VGS for transistor M1, right? Because it's all, VI is always going to be attached in some way to our signal quantity, right? Which is going to make this guy right here VF. So our feedback network is going to look something like this. All right, so tell me what my feedback network is supposed to look like. You know that that bottom node is going to be a ground. All right, so R2 will look like this. I agree. All right, so here's R1. I agree. So this is where I'm trying to trip you up. R3 isn't part of the feedback loop. R3 is the load resistor for this third stage, which is a source follower, right? Our input is here at the gate. Our output is here at the source. So this is a common drain amplifier, which should have some sort of output impedance connected here as a load. So R3 is not part of the feedback because it's telling us how stage 3 behaves as an amplifier. Told you, throwing you a curve. if I gave you something like this on an exam, I would likely just call this RS. Something to make it very obvious you're not supposed to include, but I want you to think about those things. Okay. So this is the 3-stage amplifier, right? Our first stage is a common source amplifier. Our second stage is another common source amplifier. And our third stage is a source follower or common drain amplifier. And then we have that feedback network connected. All right, so I would argue that R11, R22, and K are going to be the exact same thing it's been every other time we've seen this particular feedback network, because of course it is. Okay. So now we are going to have our open loop gain network. Here's VDD, and another, and another. RD1, RD2. All right, so here is VN. So at the source of M1, we should now see R11. And at the source of M3, so M1, M2, and M3, we're now going to have R22 in parallel with R3. And here is our output. Are we okay with representing the circuit in this way? All I'm doing is lumping R22 and R3 together into a single equivalent impedance, so I don't have to draw more stuff. All right. So our goal now is to determine our open loop gain, V out over V in. How do we do it? Yeah, so it's the gain of the first common source stage times the gain of the second common source stage times the gain of the common drain stage. Absolutely correct. So effectively, we can get a transfer function for Vx over Vn, then we can get a transfer function for Vy over Vx, and then finally we can get a transfer function for V out over Vy. Those three things multiplied together gives us our overall gain. Exactly correct. So for our first stage, what is our transfer function for Vx over Vn going to be? Exactly. Look back at your notes. That's the whole point of this crap. So what is this? Ignoring everything to the right of where my hand is doing it. Common source, because there aren't any BJTs, just to be clear. But it's a common source with emitter, now you got it, me doing it. A common source with source to generation. So GM RD1 over 1 plus GM R11, if we're neglecting channel length modulation, right? Vx over Vn GM1 RD1 divided by 1 plus GM1 R1. Oh, and actually negative, exactly right. That's very important. Okay. We'll talk about that and why it's important in just a moment. Okay. Vy over Vx.
Same thing without source degeneration.
Exactly right. So it should just be negative GM2 RD2. Yes. And then our last one is V out over Vy. So this is a source follower stage, neglecting channel length modulation. So it should be GM3 times this resistance over 1 plus GM3 times this resistance. All right, so chaining all of this stuff together, A should just be V out over Vy times Vy over Vx times Vx over Vn. So our negative signs are going to cancel each other out. So we're going to have GM1, GM2, GM3, RD1, RD2, R22 in parallel with R3, all divided by 1 plus GM1 R11 times 1 plus GM3 R22 in parallel with R3. What if I had given you a similar amplifier, as a brief aside here, where effectively just this first stage was chained to the second stage, or chained to the third stage? This part right here didn't exist. Why would that be problematic?
I'm sorry, which part?
If Vx was connected directly to here, so that this middle stage didn't exist, why would that be problematic?
Say false cascode.
The solution would still be negative.
I'm sorry, what was that from Zoom?
The solution would still be negative, the gain.
That's correct. The gain overall would be negative. If we have a negative A and a positive K, we have positive feedback, right? So we would inherently have an unstable system. That is a very good catch, whoever that was that said that. Absolutely correct. We're going to find out in some of our later examples that we're going to wind up getting negative values for our feedback factor K, which means that we have to have a negative gain in our system in order to come out with positive, a positive loop gain and therefore negative feedback. Very, very good catch. All right. Our input resistance Ri, so that's going to be this guy, is hopefully obviously infinity. And our output resistance R out is going to be what? Right, exactly right. So looking down, we see R22 in parallel with R3. Looking up, we see 1 over GM3. So that is 1 over GM3 in parallel with R22 in parallel with R3. And then at this point, we would simply plug it into our equation, right? So once we know A, we're able to determine our closed loop gain as A over 1 plus KA. Once we have 1 plus KA, we simply boost RI by that and divide R out by that, and we're good to go. All right, so how do you guys feel about these feedback voltage amplifiers? Nothing, hopefully, particularly wild or crazy, right? Once we've developed a methodology, it's just the same couple of things over and over and over. What we're going to do next week is we're going to cover the last 3 different configurations. Our feedback transconductance amplifier, our feedback transresistance amplifier, and our feedback current amplifier. We are going to do the exact same thing. The only difference that we are going to observe is that how we calculate R11 and R22 will change because our feedback network isn't in a series shunt configuration anymore. And so we're sometimes going to have port 1 short circuited and port 2 open circuited and vice versa. That's literally the only thing that's going to change our analysis. So at this point, you guys should be good to go for literally the first 5 of your 8 problems in your homework fairly easily. So I would encourage you guys to at least take a look at that and start working on it. I'm going to use the remainder of the day to continue to work on your exam. And I hope to have that posted at the absolute latest by tomorrow evening. Hope I can get it done today, but we'll see how I feel. So I think that's enough out of me for today. So enjoy the rest of your.
Real
Yes.
quick, can you go over an example similar to number 4? I ran into some issues last night trying to figure that one out.
Okay, number 4, homework problem number 4. Let me find that. Let's see, 336. Homework 6. Number 4. All right. Can you see this problem, Gregory?
Roger, I can.
Okay. So it says that an op amp has a DC open loop gain of 100 decibels and a uniform -20 decibel per decade gain roll off with a -3 dB frequency of 100 hertz. So let's unpack what that sentence means. The -20 dB per decade gain roll off means that it's a single pole system, right? Because for every pole, we should get -20 dB per decade gain reduction. So we have a single pole system where our cutoff frequency is 100 hertz and we have an open loop gain of 100 decibels. We are asked to figure out what amount of feedback is required to achieve a closed loop gain of 20 decibels. So what does, and I wrote these answers late at night, so there's always a particular possibility that I made a dumb mistake. But what would a DC open loop gain of 100 decibels, what gain would that constitute not in decibels? Let's start there.
Isn't it 10?
Pardon? 10 to the 5. Right? So if a decibel is 20 log the gain, then the gain should be 10 to the 5. Right?
That might be my issue. I think I did 10 log of the game.
So you do 10 log when you're dealing with powers, you do 20 log when you're dealing with voltages. We are specifically dealing with a voltage gain here because we're dealing with an op amp. So when we're not looking at a signal power, we're simply looking at signal voltages. So the output voltage versus the input voltage, and an operational amplifier is a voltage amplifier. That means that we should have 10 to the 5 over our amount of feedback is equal to 10.
That
So
makes
amount of
sense,
feedback
because
has to be 10 to the 4. Yeah.
makes sense, because I came up with 10 to the 8th and I was using 10 log instead of 20 log.
Yeah. So yeah, bringing that down, effectively taking the square root of that, we'll fix that then.
And then how do we go about the bandwidth?
So we simply multiply the bandwidth, the open loop bandwidth by 1 plus Ka, or our amount of feedback. So 100 hertz times 10 to the 4 should be, so that's 10 to the 2 times 10 to the 4 is 10 to the 6, which is 1 megahertz.
Okay, so the 100 hertz is the whole bandwidth. I think that was my.
Yeah, absolutely. So the reason, can I draw on this thing? Yeah, I can. Okay. So effectively, what we have is something like this, where this is the gain A, and this is the frequency F. We're at let's see, 100 decibels here. And then if this is 100 hertz, our Bode plot should look something like this, right? We're constant, and then there's our bandwidth, and then we have that roll off, where the slope of this is negative 20 decibels per decade. Well, at 20 dB, our bandwidth is extended, and we should see that it's extended to the point where we're at 1 megahertz. So whenever we have negative feedback, and we're looking at the frequency characteristics of our system, when we apply feedback, the gain is decreased by a factor of the amount of feedback, and the bandwidth is increased by a factor of the amount of feedback. Those two trade-offs happen in equal but opposite directions, effectively. Yes, ma'am. Pardon? 3 dB? Oh, problem 3, part B, sorry, yeah. All right. So if you wanted to boost the signal to noise ratio of the amplifier to 60 by replacing the preamp stage with a low noise preamp and adding negative feedback. So that went to what we were talking about in class effectively. So might have left these notes upstairs. If I did, I will fumble my way through it. Yeah, I did. And so it'll be okay though. Okay. So effectively, we have a system that looks like this. Here is our signal. Here is our mixer. This is going to be plus. This is going to be minus because we're applying negative feedback. Then we have our preamplifier. Let's call this A2. And subsequently, let's call this signal X2. And then we have a noisy amplifier. So we're going to add in some noise. Let's call this A1, which makes this X1. Here is our output node, Y. And then here is our feedback factor K, right? So let's see. We can see that Y is KX1, where X1 is equal to A2 X2 plus X noise, looking from our signal flow diagram. And then we can see that, let's see, X2 is equal to XS plus, excuse me, minus, because it's negative feedback, KY, right? So using a little bit of algebra to play around with this stuff. See, what are we going to have here? So we're going to have sorry, y isn't equal to kx1, y is equal to a1 x1. My apologies, I had a brain fart there. Knew that was looking awkward. All right, so we're going to have y is equal to a1 times x1, where x1 is a2 times x2, so that's going to be xs minus ky plus x noise, like so. Let's see, what are we going to have here? So this is going to say y is equal to a1 times a2 times xs minus a1 times a2 times ky plus a1 x noise. Anybody see anything wrong with my algebra here? All right. So that means that we're going to have y plus a1 a2 ky is equal to a1 a2 xs plus a1 x noise, and therefore y will be equal to a1 a2 xs over 1 plus k a1 a2 plus a1 x noise over 1 plus k a1 a2. That seem okay? I think we literally came to that in class. All right. So this is our signal portion, and this is our noise portion, right? So our SNR is going to be the signal portion, A1, A2, XS over 1 plus K A1, A2. And then we're going to divide that by the noise portion, which is the same as multiplying by the reciprocal of the noise portion. So that I'm going to have 1 plus K A1, A2 over A1 X noise. And that part and that part are going to cancel each other out. A1 and A1 are going to cancel each other out. And we're left with a signal to noise ratio that is simply A2 times XS over X noise. Let's call this SNRF with feedback. So this is simply A2 times the signal to noise ratio without feedback. Right? So if we want an increase of 20 decibels, we need to multiply the SNR by a factor of 10. So A2 has to be 10.